The air around you, the water you drink or play with have a lot more in common than you think. They're both fluids. According to Wikipedia, a fluid is a gas, liquid, or other item that continually deforms or flows under external force. There are two ways a fluid can flow. One is laminar flow, which is characterized by smooth paths and parallel layers of the fluid flowing. The other is turbulent flow, which is unpredictable, chaotic, has irregular fluctuations, and most of its points' velocities are continuously changing. Vortices are a major component of turbulent flow. It is a region in the fluid in which the flow revolves around a straight or curved axis. They are the regions of the fluid in which the flow revolves around a straight or a curved axis. A parameter called the Reynolds number, defined by Osborne-Reynolds, is the ratio of inertial forces to viscous forces of the fluid. Reynolds number less than or equal to 2100 indicates laminar flow, while greater than 2100 indicates turbulent flow. We all know that honey is more viscous than water. Another highly viscous fluid is pitch. In an experiment started in 1930, only 9 drops of pitch have dripped until now. Apparently, its viscosity is about 230 billion times that of water. On the other hand, ketchup is an example of a non-Newtonian fluid. The more you shake it, the thinner it becomes. In Newtonian fluids, the viscosity is independent of the pressure being applied. However, in non-Newtonian fluids, a stronger force reduces viscosity. We all saw how a path of a point helps us characterize the fluid flow type. Now let us try to trace the path of each of these points. Now comes the Navier-Stokes equation. These equations help us relate the pressure, velocity, temperature and density of a moving fluid. The first equation says that the divergence of velocity is equal to 0. The velocities in the neighboring areas of the fluid cannot be facing towards the same point or moving away from the same point. This would mean that mass is being created out of nothing or mass is getting destroyed, which is not possible. The second equation states that the acceleration of the fluid is dependent on its internal forces like pressure gradient, viscosity, and external forces as well. In a variety of experiments conducted by scientists, we have been able to use these equations to predict how a fluid will behave with remarkable accuracy. The first one is basically the conservation of mass, and the second equation is based on Newton's second law. Shouldn't it be simple? But it is one of the 7 millennium problems listed by the Clay Mathematics Institute. Then what is the problem with the math behind it? Given unique starting conditions, will we always have a solution? And if we do have a solution, will the solution be unique? And will the solution make sense in the real world? By that, what I mean is that changing the starting conditions by a little bit shouldn't mean that the solution will shoot off to infinity. That wouldn't make sense in the real world, will it? Maybe you guys could solve this equation one day.